Hello, welcome back to my channel. So we're going to be talking about determining absolute versus conditional convergence. So absolute and conditional convergence are totally dependent on the series that we have. So let our series of a sub n be an infinite series. If the summation of those terms, if we take the absolute value of it and it converges, then that series is absolutely convergent. If we take if the series converges when it's not absolute value, but it diverges when it is absolute value, we call that conditionally convergent. So let's look at what we have here. We have 1 over n, or 1 over n squared. This is a p-series. Where p is equal to 2. Because 2 is bigger than 1, we know this converges. So now what we need to do is we need to look at anything that would need a absolute value. So if we took the absolute value of this, it's not going to matter, but what would matter is if we have that alternating series. So if I have an alternating series of 1 over n squared, so I have n negative 1 to the n power divided by n squared, so that's our alternating series of that p-series. So what we're going to do is we're going to now look at the absolute value of this. So if we look at the absolute value of it, we have the summation of the absolute value of our function here. This absolute value is literally going to just take away that entire piece of that alternating series piece. So we are still looking at 1 over n squared. We just said that converges. So what we know is this series of our negative 1 to the n over n squared is absolutely convergent. So because this converges, we know overall we have something that is absolutely convergent. And so it just means that it doesn't have any conditions for when it converges, being just positive values or positive or negative values. On the other hand here, if we look at the harmonic series, we know the harmonic series diverges. Its counterpart, the alternating harmonic, we looked at earlier, and by the alternating series test, we found out that this converges. So if we were to look at the series in itself and think about the fact that the absolute value of this series is the same thing as the harmonic series, which diverges, we know the original series, the alternating series, is going to be conditionally convergent because its original series, the harmonic, is divergent. So realistically speaking here, when we're looking at these, we're going to be looking at alternating series, and those are going to be the ones that we're going to decide if they're absolutely, conditionally, or diverge. So we're going to look at a problem here, and it says, does the series converge absolutely or conditionally, or diverge? So saying it converges now isn't the only thing that we can do. So now we have to use those tests for if our series converges or diverges, but now we also need to look at it in the absolute values case. So the first thing that we're going to do here is we're going to decide if this function converges or diverges. And the reason why is because if we say that this diverges, then we don't even need to look at the rest of this, because this is only if it converges, then we look at the absolute value. And if we look at the absolute value and it converges, then it's absolutely convergent. So we're going to decide if the function as it stands is convergent. It's an alternating series, so we're going to use that alternating series test. So the first thing that we want to do is we want to claim a sub n. So a sub n is going to be 1 over the cubed root of n, which means we're going to go ahead and change that out. So we want it to be n to a singular power. So we're going to get it out of the denominator, and we are going to get it into a fractional exponent to get n to the negative 1/3 power. So now we want to use that alternating series method. So the first thing that we need to do is we need to decide if the limit as n approaches infinity of our function n to the 1/3 power, or negative 1/3 power, or 1 over the cubed root of n is going towards 0 or not. This is a Bobo case. It's bigger on bottom, so we are going to 0. The next thing that we need to decide is, are those terms getting smaller or they're non-increasing? So we need to make sure that a sub n is bigger than or equal to a sub n plus 1. So I have 1 over n to the 1/3 less than or equal to 1 over n plus 1 to the 1/3. So just like the other times, we're going to multiply both sides by the denominators. So I have n plus 1 to the 1/3 greater than or equal to n to the 1/3. So the cube root of a slightly bigger number is going to be bigger than or equal to a number cubed, or the cubed root of a number. So we know that this works for all n, because we're looking at positive n values. So what this tells us is, by the alternating series test, the summation from n equals 1 to infinity of negative 1 to the n over the cubed root of n converges by the alternating series test. So now what we need to do is we need to look at the absolute value of this. So we're going to look at the summation from n equals 1 to infinity of the absolute value of negative 1 to the n divided by the cubed root of n. This is going to give us the summation from n equals 1 to infinity of 1 over the cubed root of n, or 1 over n to the 1/3 power. When we look at this, we have to notice that it's a p series, where p is equal to 1/3. 1/3 is less than 1, and because it's less than 1, we know that this diverges. So diverges by the p series test. So we converge when we're looking at it in negative versus positive terms, but it diverges when it's in the absolute value form. So we know that this series from 1 to infinity, that alternating, is conditionally convergent. So the main things here are, we need to look to see if our alternating series is going to converge conditionally or absolutely. We could potentially look at the absolute value of it first to decide what to look at. If the absolute value is convergent, then it's going to be absolutely convergent. But we're not always guaranteed that. So sometimes it's easier to just look at it one piece at a time. Because you may have to do the alternating series test on here anyways, because it was conditionally convergent.